1,3-butadiene is a simple conjugated diene with the formula C4H6. It is an important industrial chemical used as a monomer in the production of synthetic rubber. The word butadiene usually refers to 1,3-butadiene, which is the structure H2C equals CH equals CH2. Although butadiene breaks down quickly in the atmosphere, it is nevertheless found in ambient air in urban and suburban areas as a consequence of its constant emission from motor vehicles. The EPA lists it as the mobile source air toxic with the highest normalized risk factor, exceeding that of formaldehyde, the second riskiest air toxic emitted by motor vehicles, by a factor of more than 20. The name butadiene can also refer to the isomer, 1,2-butadiene, which is accumulated diene with structure H2C equals CH3. However, this alone is difficult to prepare and has no industrial significance. This diene is also not expected to act as a diene in a Diels-order reaction due to its structure. To effect a Diels-order reaction, only a conjugated diene will suffice. The rest of this article concerns only 1,3-butadiene. History. In 1863, the French chemist Ethanol isolated a previously unknown hydrocarbon from the pyrolysis of amyl alcohol. This hydrocarbon was identified as butadiene in 1886, after Henry Edward Armstrong isolated it from among the pyrolysis products of petroleum. In 1910, the Russian chemist Sergei Lebedев polymerized butadiene, and obtained a material with rubber-like properties. This polymer was, however, found to be too soft to replace natural rubber in many applications, notably automobile tires. The Butadiene industry originated in the years leading up to World War II. Many of the belligerent nations realized that in the event of war, they could be cut off from rubber plantations controlled by the British Empire, and sought to reduce their dependence on natural rubber. In 1929, Eduard Skornka and Walter Bock, working for IG Farben in Germany, made a copolymer of styrene and butadiene that could be used in automobile tires. Worldwide production quickly ensued, with butadiene being produced from grain alcohol in the Soviet Union and the United States and from coal-derived acetylene in Germany. Production extraction from C4 hydrocarbons in the United States, Western Europe, and Japan. Butadiene is produced as a byproduct of the steam cracking process used to produce ethylene and other olefins. When mixed with steam and briefly heated to very high temperatures, aliphatic hydrocarbons give up hydrogen to produce a complex mixture of unsaturated hydrocarbons, including butadiene. The quantity of butadiene produced depends on the hydrocarbons used as feed. Light feeds, such as ethane, give primarily ethylene when cracked, but heavier feeds favor the formation of heavier olefins, butadiene, and aromatic hydrocarbons. Butadiene is typically isolated from the other four carbon hydrocarbons produced in steam cracking by extractive distillation using a polar aprotic solvent such as acetonitrile, and methylpyrrolidone, furfural, or dimethylformamide, from which it is then stripped by distillation. From dehydrogenation of N-butane . Butadiene can also be produced by the catalytic dehydrogenation of normal butane. The first such post-war commercial plant, producing 65,000 tons per year of butadiene, began operations in 1957 in Houston, Texas. Prior to that, in the 1940s the U.S. War Department constructed several plants in Borger, Texas, Toledo, Ohio, and El Segundo, California to produce synthetic rubber for the war effort as part of the United States Synthetic Rubber Program. Total capacity was 68 kmta. Today, butadiene from N-butane is commercially practiced using the Hydrocarbons process, which was developed during World War II. From ethanol in other parts of the world, including South America, Eastern Europe, China, and India, butadiene was also produced from ethanol. While not competitive with steam cracking for producing large volumes of butadiene, lower capital costs make production from ethanol a viable option for smaller capacity plants. Two processes were in use. In the single-step process developed by Sergei Lebedev, ethanol is converted to butadiene, hydrogen, and water at 450 degrees Celsius over any of a variety of metal oxide catalysts. 2CH3CH2OH CH2 equals Car CH equals CH2 plus 2 hours 2O plus H2. This process was the basis for the Soviet Union's synthetic rubber industry during and after World War II, and it remained in limited use in Russia and other parts of Eastern Europe until the end of the 1970s. At the same time, this type of manufacture was cancelled in Brazil. Nowadays there is no industrial production of butadiene from ethanol. Lately Lanxess has announced plans to produce butadiene from ethanol. In the other, two-step process, developed by the Russian émigré chemist Ivan Ostromyslinsky, ethanol is oxidized to acetaldehyde, which reacts with additional ethanol over a tantalum-promoted porous silica catalyst at 350 degrees Celsius to yield butadiene, CH3CH2OH plus CH3CHO as CH2 equals Car CH equals CH2 plus 2 hours 2O. This process was one of the three used in the United States to produce government rubber during World War II, though it was not preferred because it is less economical than the butane or butene routes for the large volumes needed. Still, 3 plants with a total capacity of 200 kmta were constructed in the U.S. with startups completed in 1943. The Louisville plant initially created butadiene from acetylene generated by an associated calcium carbide plant. The process remains in use today in China and India. From butanes 1, 3-butadiene can also be produced by catalytic dehydrogenation of normal butanes. This method was also used by United States synthetic rubber program during World War II. The process was much more economical than the alcohol route but competed with aviation gasoline for available butene molecules. The USSRP constructed several plants in Baton Rouge and Lake Charles, Louisiana, Houston, Baytown, and Port Neches, Texas, and Torrance, CA. Total annual production was 275 kmta. In the 1960s, a Houston company known as Petrotex patented a process to produce butadiene from normal butanes by oxidative dehydrogenation using a proprietary catalyst. It is thought to be no longer practiced commercially. After the WWII, the production from butanes became the major type of production in USSR. For laboratory use 1. 3-butadiene is inconvenient for laboratory use because it is a flammable gas subject to polymerization on storage. 3-butadiene cyclic sulfone is a convenient solid storable source for 1,3-butadiene for many laboratory purposes when the generation of sulfur dioxide byproduct in the reaction mixture is not objectionable. Most butadiene is polymerized to produce synthetic rubber. While polybutadiene itself is a very soft, almost liquid material, copolymers prepared from mixtures of butadiene with styrene and/or acrylonitrile, such as acrylonitrile butadiene styrene, acrylonitrile butadiene and styrene butadiene are tough and/or elastic. SBR is the material most commonly used for the production of automobile tires. Smaller amounts of butadiene are used to make the nylon intermediate, adiponitrile, by the addition of a molecule of hydrogen cyanide to each of the double bonds in a process called hydrogenation developed by DuPont. Other synthetic rubber materials such as chloroprene, and the solvent sulforlane are also manufactured from butadiene. Butadiene is used in the industrial production of 4-vinyl cyclohexane via a Diels-Alder dimerization reaction. Vinyl cyclohexane is a common impurity found in butadiene upon storage due to dimerization. Cyclooctadiene and cyclododecatриene are produced via nickel or titanium catalyzed dimerization and trimerization reactions, respectively. Butadiene is also useful in the synthesis of cycloalkanes and cycloalkanes, as it reacts with double and triple carbon-carbon bonds through the Diels-Alder reaction. Environmental health and safety. Acute exposure results in irritation of the mucous membranes. Higher levels can result in neurological effects such as blurred vision, fatigue, headache and vertigo. Exposure to the skin can lead to frostbite. Long-term exposure has been associated with cardiovascular disease. There is a consistent association with leukemia, and weaker association with other cancers. 1. 1,3-butadiene is listed as a known carcinogen by the Agency for Toxic Substances Disease Registry and the U.S. EPA. The American Conference of Governmental Industrial Hygienists lists the chemical as a suspected carcinogen. The Natural Resource Defense Council lists some disease clusters that are suspected to be associated with this chemical. Some researchers have concluded it is the most potent carcinogen in cigarette smoke, twice as potent as the runner-up acrylonitrile. 1,3-butadiene is also a suspected human teratogen. Prolonged and excessive exposure can affect many areas in the human body. Blood, brain, eye, heart, kidney, lung, nose and throat have all been shown to react to the presence of excessive 1,3-butadiene. Animal data suggest that women have a higher sensitivity to possible carcinogenic effects of butadiene over men when exposed to the chemical. This may be due to estrogen receptor impacts. While these data reveal important implications to the risks of human exposure to butadiene, more data are necessary to draw conclusive risk assessments. There is also a lack of human data for the effects of butadiene on reproductive and development shown to occur in mice, but animal studies have shown breathing butadiene during pregnancy can increase the number of birth defects, and humans have the same hormone systems as animals. Storage of butadiene as a compressed, liquefied gas carries a specific and unusual hazard. Over time, polymerization can begin, creating a crust of solidified material inside the vapor space of cylinder. If the cylinder is then disturbed, the crust can contact the liquid and initiate an autocatalytic polymerization. The heat released accelerates the reaction, possibly leading to cylinder rupture. Inhibitors are typically added to reduce this hazard, but butadiene cylinders should still be considered short shelf-life items. The hazard presented by popcorn polymer is also present in bulk commercial storage tanks. It is important to keep the oxygen concentration in the tanks and any process wash water low in order to reduce the rate of polymerization. As with other light hydrocarbons, butadiene leaks can be detected by the formation of ice balls even when the temperature is well above 0 degrees Celsius. 1,3-butadiene is recognized as a highly reactive volatile organic compound for its potential to readily form ozone, and as such, emissions of the chemical are highly regulated by TCEQ in parts of the Houston-Brazoria-Galveston ozone non-attainment area. 1. See also, cyclobutadiene, polybutadiene, hydroxyl-terminated polybutadiene. References. External links. 1,3-butadiene Euro Agency for Toxic Substances and Disease Registry. 1,3-butadiene Euro CDC, NIOSH Pocket Guide to Chemical Hazards, National Pollutant Inventory Euro 1,3-butadiene.